On this week's MetPy Monday, it's all about compression. How can we use Python to automatically zip up or make tarballs from files that we have on our disk that we may not want to store in uncompressed form? Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, we're going to sort of continue the theme we had last week. So last week, we talked about how to make your images from Matplotlib smaller by opening them using Pillow and resaving them with a little bit tweaking of the color palette. This week, I want to look at any file and how we can compress it, or a series of files. Now, we've all heard about zip files or tarballs. So we're going to look at ways that Python can make those for us, compare their performance relative to each other, and try to compress several different types of files to see what kind of results we get, where you might be able to get good use out of compression, and where compression's probably not going to help you. So I'm going to import shutil. And from pathlib, I'm going to import the path object. So what I want to do is provide a folder to a function that I'm going to write, find out what's the size of the contents of that folder, and then I want to try compressing it with several different techniques and print out the size of each of those techniques as a result, and then we can compare them. Now, I have 4 different folders that I want to do this test on. That's why I want to write this as a function, so I don't have to copy and paste blocks of code. Remember, if you're copying and pasting blocks of code, that's a really good indication that you should be writing a function. I have a folder of grib files that we want to try to compress, folder of netcdf files, a folder of a few thousand maps, like those that we made in last week's video, and a folder of large text documents. So say a set of METAR archives or Mesonet archives. So I'm going to write my function starting with the keyword def, compress, folder, and check sizes. And it's going to take one argument, which is my folder. We'll use triple bad quotes because we always write a docstring because we're kind to ourselves and we practice empathy-driven development, which is you don't write something that's undocumented. You know what it does now. In 6 months, you won't. This function compresses the contents of folder using several different techniques and compares the sizes in printouts. All right. So first we need to print the size of the contents of the folder. And surprisingly, there's not a really straightforward cross-platform way to do this. So we're going to have to use a little bit of magic here. And by magic, I mean we're going to use a list comprehension. I want to write the sum. What do I want to take on an individual file? We saw this last week. File.stat.st_size for every file in what? In the file list that's in our folder. So I'm going to create a path object for folder and use the recursive glob on the wildcard. Okay, so what does all this mean? And we close our sum parentheses. So for file in any file matching anything recursively in our folder, I'm going to get the size of that file, and I'm going to add it through the sum function. So we get the sum of all files in that folder. Now I used bad quotes here because I'm going to put this in a print statement using an f string that says the raw file size is this sum. So we're going to need to put that in curly braces. So I'm going to divide by 1024 to get from bytes to kilobytes. And then again, because we want to go from kilobytes to megabytes. A little bit more easy to parse unit for what we're going to be working with. And I want to print that with 1 digit after the decimal floating point, megabytes. Close my single quote, close my print. Okay, so that gives us the sum of all the files in the folder, our starting point. Now for compression type and extension, file extension, and we're going to use the zip function. Now this is not zipping the file. This is stepping through 2 lists together in lockstep. And now we need to give it the compression types and the file extensions to expect. The compression types that we're going to try are zip, tar, gztar, and bztar. The file extensions for those are zip, tar, tar.gz, and tar.bz2. Now we actually need to do the compression. shutil, make archive. First we're going to give it the folder underscore compressed. So this is going to be the output. The compression type that we want to use, which is comp type, and the path to our input, so our folder. Now, make archive automatically adds the file extension for us. That's why I didn't put it in the F string there. So it will, if our folder is called Bob, it's going to create Bob underscore compressed dot zip. Now the next iteration, Bob underscore compressed dot tar, and so on. Now we're going to do another print. I'm going to print the file extension so we see what extension we're working with here. I'm going to create a path object using double quotes now that we're inside this first F string, because we're creating a second F string, to the folder underscore compressed dot extension dot stat dot st size divided by 1024 twice, formatted as a floating point with 1 number after the decimal or 1 numeral, megabytes. Close the first F string, close the print. Now let's try our new function, see if we have any typos or any logical fallacies in here. My first folder is grib to compress. So our raw grib folder is almost 223 megabytes. And now it's going to take a little bit to do these various compressions. We see a zip is 157. So we get a pretty significant savings there, close to 25%. Tar doesn't do anything. And we'll see what tar.gzip and bz2 do. Now the reason that tar is not doing anything, so zip actually looks in the folder and takes every file, compresses it, and adds it to an archive. Tar stands for tape archive, to give you a little bit of the idea of how old this command is. And it's taking all of those files and serializing them like we would want to record them on a tape drive. But it's not doing any compression. So we then pipe the output of tar into a compression algorithm, such as gzip, which we can see gets us down just slightly below what zip did. A little less overhead with working with that one stream. And then bz2, another compression, gets us another 10 megabytes down. So in this case, tar.bz2 saved us a pretty significant volume. But grib is binary, that it will compress, but it's not incredibly compressible. So we're going to try this on some other file types. netcdf, of course, is a very common file type for people in our community to be dealing with. The map images like we made last week. And and text. So we can see the netcdf doesn't compress much, which makes sense. netcdf is a compressed binary format. So we're trying to optimize something that's already pretty optimized. We see we gained the most advantage from zip and gzipped tars, but only saving us about 4 megabytes out of that 124. The maps, remember these are already pretty optimized PNG images from our MetPy Monday last week. So tar actually inflated it slightly. Gzipped tar was a few megabytes better. A zip was a few megabytes better. And the BZ2 tar, we'll see, I would expect it to be very similar. Again, these just aren't compressing that well because we've already done a pretty good job of optimizing the file storage. Okay, so that saved around 20 megs. The text, our raw text, is 10.6 megs. Zip gets us down to 3.1, the same as tar.gz. Tar very slightly inflates it. And the BZ2 tar actually gets us down to 2.5 megs. So that's about a 5 times reduction. So text compresses very nicely, especially numeric data with many similar values, such as Mesonet, Surface Obs, METARs, those sort of things. So while not all of your files can benefit from this, using shutil to make archives or extract archives can save you a significant amount of disk space. And if you're uploading these things to a remote server, you're just transferring that one compressed file as opposed to many transfers of small files. I hope that you found this useful, and I'll see you on next week's MetPy Monday.